G'day, it's Mr. Kane here, and we're going to look at some stuff about telescopes in this little video clip. I remember as a lad being taken out in the backyard with my dad. He'd borrowed a telescope and we spent some time looking at the moon, and I can remember seeing so clearly the mountains on the moon and the craters and things so clearly. But the best moment, the wow moment, was when we looked at Saturn and I first saw the rings of Saturn with my own eyes. That was something special. And I'm really pleased being able to do the same thing for my kids. I've borrowed a telescope from the school where I work and taken it home, and it's still that wow moment when I get to see the rings of Saturn. There's something special about that. I hope you guys get the chance too. But how about we go look at how these things actually work and what's going on. So refracting telescopes are the ones we're going to look at first. These are the sort of the classic ones you see the pirate captains looking at across the oceans through. And they're attributed to being first made by Galileo back in the 1600s. And he got himself in trouble with these things because he changed a whole lot of what we knew about the universe. Prior to his looking through telescopes, we thought that the Earth was at the centre, and it's not. And that got him in a spot of bother with the powers that be, and they actually stuck him under house arrest for a number of years. And but it was clear to him that what he saw with the telescope, that we were not at the centre. He also saw that other planets had moons that orbited around them. It wasn't all orbiting around the Earth. Prior to that, we thought that it all was. That's what the people were taught. But he saw that other planets had moons. For example, there's a photo of a moon of Saturn. You can see Saturn in the background. So we had to change the maps. They had to have maps like this, with the Earth at the centre and all the other known planets orbiting around it. So they started coming with maps like this, with the Sun at the centre, and Earth and the other planets that we could see orbiting around that. But now we've got telescopes, we can see more planets than that. And we've got diagrams like this that show photos of other planets in their place in space. Although this is not to scale, both size and distance. But how do we go about looking at them? So what do these things have in common? This is the Hubble Space Telescope. That's a contact lens. That's a refracting telescope that you can buy in a shop, or the school where I work has one pretty much the same as that. And that's the eye that you have. All these things have a lens in them somewhere. And we use the lenses to help us see things far away. So what are they doing? The light's coming in, it's being gathered by the lens, and the lens is concentrating it to a focal point. Now this diagram's not 100% accurate. I couldn't get my computer trickery to work that for me. I'm a bit limited there. But we have the light ray should, when it hits the surface of the lens, go straight across to the other side. Okay, it doesn't kink in the middle. It actually bends when it hits the surface of the lens, right here at the surface, and it bends again when it comes out the other surface. Through there, it'll go straight line across at a slight angle. So it refracts or bends the light. And that's what a refracting telescope does. It has several lenses in it. This is a simple diagram showing just a couple in there. The first one, all the light comes through our objective lens, gathers and focuses it to the eyepiece lens, and then on to the pupil of our eye. So what's actually happening at each point in the way on the journey through? So the objective lens, it's gathering the light and it's bending it into focus. So all the light, the dim light from a dim star, is being gathered together and concentrated to the focus point. Okay? So it's all bent to a bright point, concentrated there, like you do with a magnifying glass when you're taking the sunlight and burning a hole in a bit of paper or something. And then the next lens refocuses it to the size of our eye's pupil so we can see it clearly. So that dim light's being concentrated and sent into our eye so we can see dim, faraway objects quite easily. Now this is a refracting telescope, so it's bending light to do that. There's a limit though to how big we can make these things. After a certain size, the lenses get so big that their own weight distorts things a little bit. which isn't good enough for us seeing out into space. So we've gone bigger by using a reflective telescope. With these, they use a big mirror. Okay, at the very bottom of the telescope, down here, this thing here is a big mirror, and we can make mirrors a lot bigger because we can support their weight in a big framework in the back here. And all the big telescopes around the planet are reflective ones. So the light comes in, hits the mirror in the back, and is concentrated to another mirror inside, which sends it out through the eyepiece. Now, strangely enough, even though in the middle of the telescope you have this mirror sitting in the middle of where the light is coming through, it doesn't affect the image that comes out to your eye. Our brain is able to sort of block it out. You know, we've got one at the school where I work, and you can see clearly from the outside the thing sitting in the middle, but when you look at the image, it's not there. So, two types of telescope, refractive and reflective, and all the very large ones, they are reflective. So they use light to help us explore space. So we can see things like this, a galaxy, things like that, which is the gas ring around an exploding star, a supernova. But you see how it's a little bit fuzzy around the edges? That's the issue with looking out through our atmosphere. It distorts things a little bit. So we've done things like putting telescopes into a plane. So this is the Sophia plane, and it comes to where I live in Christchurch, New Zealand, roughly once a year in our winter time, and it flies high in the atmosphere to observe what's going on through the infrared spectrum of things. And it's a converted ex-Pan American jumbo jet, and I'm not sure you can see it clearly in the photo, but here at the back of the plane there's a slight bulge in the fuselage. There's actually a door here that opens in flight, and it slides around that way. It's completely circular, the whole fuselage here. The fuselage is circular, so the door slides around it, and they've got some fairings to stop the wind coming in. In fact, they've done it so well that when the pilots in the cockpit up here actually have a light that tells them when the door is open, because they can't detect it when they're flying. So they get up to altitude above the atmosphere, open the door in the plane, and observe things way out in space above the worst of the dust and distortion in the atmosphere. And that's a look inside the plane at what you can see from the telescope on the inside. It's not very much, it's all behind a big pressure bulkhead. So that's getting above most of the atmosphere. Now we've done better than that as well. We've gone actually out into orbit, and this is the Hubble Space Telescope right above the atmosphere, giving us some super clear images of things out in space. So, for example, here's my favourite planet again, Saturn with its rings. And it also takes images like this, not just with visible light, but using ultraviolet and infrared. There, for example, is ultraviolet of Jupiter. So this is using types of light, visible and the light that we can't see, but infrared and ultraviolet light that we can't see, but we can still see more details. Now we can see more details now by using other ranges from the electromagnetic spectrum that light is part of. We can use radio telescopes. So many things, they're emitting radio waves. So we're emitting radio waves off this planet with our TV and radio and telephone signals, but other planets like Jupiter and other things out in space also emit radio waves, and we can see them with radio telescopes and learn a whole heap more about them. So there's an example of a radio telescope, 76 metres across, a place called Jodrell Bank. Now there's a really good movie called The Dish. It's about a radio telescope that's in Australia, and it's set up. The dish is set for when the time there was when the man first walked on the moon. It's quite an enjoyable movie. I enjoy the scene where they're actually up on the dish, and they're playing cricket on the dish, which is quite a hard case. So there's Saturn with visible light, and there's Saturn in radio wavelength light. So we get more information and add more to our knowledge by looking through all the wavelengths of what's coming from different planets. So I really hope that you can too one day get out of the backyard, look up at the sky through a telescope. You see a whole heap more, and if you pardon the